Good morning. My name is Kevin Hetrick. I'm the Central Indiana Area Manager for Clark Dietz. I don't know where everyone else is located, but we're expecting a foot of snow here today in Indianapolis. Clark Dietz is a Midwest engineering firm serving Indiana, Illinois, Wisconsin, and Kentucky. Prior to working at Clark Dietz, I was a project manager with the Indiana Department of Transportation. And the project I'll be discussing today was from my time at INDOT. Project is Milton Madison Bridge, a major rehabilitation and reconstruction of an Ohio River bridge connecting Madison, Indiana, and Milton, Kentucky. On the project, extensive pier and foundation testing and analysis during design allowed for pier and foundation reuse, cutting project costs by nearly half. I'd like to start by giving credit to the many project partners who made the project a success. INDOT and the Kentucky Transportation Cabinet were committed to restoring the bridge to like new condition. Many of the items discussed in today's presentation required federal highway approval. The project was eventually procured as a design build. That team was led by Walsh Construction, with Buckland and Taylor as the engineer of record for the truss superstructure, and Burgess and Nipel serving as the engineer of record of the pier rehab that I'll be discussing today. Working for INDOT and KYTC, Michael Baker were our lead technical experts, and many of the ideas addressed in today's presentation are credit to the engineers at Michael Baker. Last but not least, CDM Smith led the environmental process on behalf of the two states. Milton Madison Bridge is located approximately halfway between Louisville and Cincinnati and is a vital connection for the people of Madison, Indiana, and Milton, Kentucky. There are only two bridges in the 110-mile stretch of river between Louisville and Cincinnati. Any bridge closure would require a 50-mile detour for the users of Madison and Milton. Two towns largely operated as one town. The users use the bridge daily to go to work, to see their families, to shop for groceries. Closing this bridge is going to be a major inconvenience for the local users. Unfortunately, the bridge is getting very old. When we started working on this project, it was 2009. The bridge was built in 1929, making it 80 years old. As a steel truss bridge, especially in the Midwest, an 80-year-old truss was starting to be in pretty rough condition. It needed routine maintenance, which required occasional closures and detours. And it was the condition of the bridge is a major concern for the locals, but also for INDOT and the Kentucky Transportation Cabinet. You can see a couple pictures on this slide. The bridge was running out of time. Many of the steel truss members were corroded all the way through. The load rating had been dropped to 15 tons. Then just as we were starting construction in 2011, the states decided to drop the load rating all the way to 3 tons. The bridge was also very narrow. I mean, built for the vehicles in 1929. Only 10-foot wide lanes, 20-foot wide total curb to curb. Had a lot of crashes on the bridge. It was a daily safety concern. A lot of side view mirrors being swiped. Looking to provide a reliable crossing for the two towns, in 2009, INDOT and KYTC had undertaken an environmental assessment. Many new alignment alternatives were explored, but also an alternative that was looked at was keeping the bridge on the existing alignment. Keeping the bridge on alignment offered a path of least resistance, as both Madison and Milton included large historic districts. The Section 106 consultation was extensive, involving parties in both states and Washington, D.C. There are many challenges to keeping the bridge in alignment, though. For one, to construct a new bridge in the existing alignment, the bridge would need to close during construction, which is going to be a big inconvenience for users. Also, it wasn't clear how viable it was to reuse the piers. In 2009, the federal Tiger Grant program came out, which was intended to award funds to shovel-ready projects. For Milton Madison, the superstructure replacement with minimal approaches alternative could be shovel-ready. No right-of-way was required. Staying on existing alignment simplified our NEPA and permitting processes. So the states moved forward with the project as a design build, applied for a Tiger Grant, and received $25 million, with the goal to have the project under construction approximately 18 months later. The existing bridge has 5 spans across the Ohio River. The alternative to reuse existing piers would reduce that to 4 spans. 4 existing piers would be encased with new concrete and strengthened. New pier caps would be constructed, and a new pier would be constructed on the Indiana shore, replacing 2 existing piers. With the pier rehabilitation alternative, the Coast Guard had confirmed that the navigation channel could remain as is, which is a big victory for the project, as a new bridge was going to require a much larger navigation channel, which was going to drive up project costs considerably. While the piers are mostly staying the same as existing, the truss superstructure is planned to receive a major overhaul. Existing 10-foot wide travel lanes with no shoulders would be expanded to 12-foot wide. Shoulders would be added to provide space for broken down vehicles and to maintain traffic during inspections and maintenance. A sidewalk was planned to be cantilevered off the downstream end of the truss. In total, the width of the truss was more than doubling from the original condition. The wider footprint, additional dead load, and eccentric forces from the significantly larger superstructure were a unique challenge for pier reuse. In assessing the viability of reusing the piers, several goals were set to determine what a successful pier rehabilitation would consist of. First, the two states wanted a like new bridge. This was a big investment, and we were looking for 75 years of service life. Budget was a big consideration. Could a pier rehabilitation solution provide the cost savings we were looking for to fit within the $100 million budget? Also, the piers to be permittable. The U.S. Coast Guard had concurred with maintaining the 727-foot wide navigation channel, but we had to make sure not to reduce that. And finally, the piers need to be acceptable to historic consulting parties. The city of Madison includes a 2,000 building historic district, and Section 106 consultation was extensive on the project. One challenge to doubling the size of the truss from 24 feet to 48 feet was that the existing piers were tapered to carry a 24-foot wide truss. The new truss was going to require a much wider pier cap. To do that, we're just going to pour concrete shell around the existing pier while the bridge was still in service. Then she construct a new pier cap, remove the truss, and build a new truss on top of the widened pier cap. A lot of the work would be able to happen while traffic was still on the bridge, but eventually the bridge would need closed to reconstruct the truss. Knowing what the end product needed to look like still required a lot of engineering to confirm there was a viable, cost-effective alternative to reuse the piers. The engineers on the project started by researching the original plans, reviewing the 1929 plans, but also reviewing construction photos and press accounts from the time. The foundation of the bridge was constructed as a pneumatic caisson. As shown in the picture in this slide, a steel chamber was constructed on shore. The chamber included 2 airlocks. Once the chamber was completed, it was floated into place and sunk to the bottom of the river. From there, wooden forms and concrete were constructed on top of the caisson. Workers entered the airlocks, and as they excavated material, the caisson sank deeper into the river bottom. This was continued until the caisson sank to the bedrock. The foundation was socketed into the shale bedrock below. With the caisson fully embedded in the bedrock, wood forms were installed from the river's bottom to above the water level. Concrete was poured through the airlocks into the caisson, filling both, after which construction of the pier stem started. It's worth noting that with this construction method, there was no reinforcing in the original caisson, which certainly became a challenge to determine if the piers could be reused. So next step, reinforcing steel was doweled 12 feet deep into the unreinforced caisson. Wooden forms were installed inside the caisson forms, and a reinforced pier stem was erected going up from there. The original construction, as noted previously, there was no reinforcing in the caisson, unless you count the airlocks. The pier stem was significantly under reinforced by today's design standards. Knowing what we knew about the original bridge and how it was built, our team set out to get a better understanding of the current condition of the bridge. 2 cores were taken from each pier, drilling through the deck, the pier stem, the caisson, all the way down into the bedrock. Geotechnical borings were also taken of the river bottom around each pier. The total depth of the cores approached 200 feet in length. The slide shows a small portion of the samples taken from the piers. The top and bottom of the caisson are apparent in these pictures. All samples were sent to the lab for testing. The strength of the concrete was very good. Much of the piers in the caisson had been underwater for 80 years, and some samples approached strengths of 10,000 psi. Chloride content for most piers is acceptable, other than one pier on the Indiana approach had been exposed to years of de-icing. That pier, as previously noted, was removed and replaced with another pier, a new pier, on the Indiana banks. Arm's length inspections were performed of each pier. Crews looked for visual defects that weren't apparent, like spalling, honeycombing, or reinforced steel. And they sounded the bridge to look for delamination or voids. Underwater inspections were also performed of each pier and geotechnical borings taken of the soil in each location. If the pier is going to be incorporated into the new design, both states wanted to ensure the existing piers were in very good condition. The geotechnical borings revealed that the river soils consist of approximately 60 feet depth of sand and gravel. The layer also featured heavy boulders at the bottom. Bedrock was mostly shale with limestone. The original caisson was socketed into the rock approximately 2 to 7 feet. There's a 70-foot height of unreinforced caisson extending up from the bedrock, and nearly 100 feet of unreinforced pier stem above that. At that point, we had resolved that the piers were in good condition for the way they were built. Knowing that the piers were in good condition was only a small piece of the puzzle. In addition to building a much larger truss in these piers, modern design loads to be considered were much more extensive than the loads considered in 1929. Those loads include a dead load from a heavier truss, modern codes for wind loading, larger live loads and braking loads from today's heavy vehicles, increased weight from new pier concrete, and vessel collision, a factor that was completely not considered in the original design. The engineers on the team also had many concerns to address relative to how the new and old concrete perform in a composite manner. There were concerns with how the bearing loads would act on the widened pier cap. Tension in the under-reinforced stem and the interface with the caisson were definite challenges. And tension in the unreinforced caisson was something that definitely needed addressed. Last but not least, consideration needed to be given to the underlying soils and their stability to handle the demands. There's a general understanding that designing the rehabilitated piers using standard vessel impact and wind loads will result in expensive foundation improvements that would make the superstructure replacement alternative cost prohibitive. With the piers needed designed to withstand modern load combinations, the engineers in the project worked to determine risk-based loading criteria instead of relying on deterministic load requirements. One method to do that was to use method 2 from AASHTO's vessel collision specification. Between 40,000 and 60,000 barges per year use the Ohio River at Milton, Madison. Close coordination was undertaken with Federal Highway, the U.S. Coast Guard, and the U.S. Army Corps of Engineers to determine the water levels, size and number of barges, and the classification of the bridge for a method 2 barge analysis. Milton Madison was classified as a regular bridge with acceptable annual frequency of collapse of 0.001, the number of vessels, the likelihood of an aberrant barge, the geometric probability of vessel impact, and the likelihood of collapse due to an impact were all considered to determine the required pier capacity that was needed to withstand barge impact. Water levels for various flood events were coordinated with the Army Corps. 2 different barge impact events were considered: an adrift barge floating at the 100-year flood elevation, and the second was a fully loaded barge traveling downstream at mean high water. Results of the study provided impact forces to be used to determine the required pier capacity for vessel collision, as detailed in the table, this table that's taken from the project's vessel collision study. The study provided the project with acceptable risk-based criteria that would provide for a long-lasting bridge while also controlling project cost. Complying with this document eventually became a requirement that we put on the design builder. The other major lateral load that the project engineers sought to refine was wind loading. Towards this, the project contracted with Rowan, Williams, Davies, and Irwin to perform a site-specific wind study. RWDI performed a statistical wind climate analysis to determine site-specific wind speeds using 60 years of available data from the Louisville and Cincinnati airports and 35 years of data from the Lexington, Kentucky airport. RWDI simulated the terrain and surface conditions to develop a 3D model of the bridge site. Directionality of the wind was considered, and turbulence properties for wind in the corridor were assessed. At their Ontario labs, RWDI performed static 2D testing with 3D wind tunnel testing to gain an understanding of the site and also the aerodynamic stability of the bridge. And as a result of the project-specific wind study, we were able to use wind loading that was significantly reduced from the conservative wind speeds required by code. The project-specific wind speeds were able to be reduced by up to 30%, while providing an accurate picture of the conditions that the bridge was likely to be exposed to. 1 hour wind speeds were provided for design loads, while 10-minute wind speeds were provided to check stability. Based on RWI's calculated wind speed and their lab modeling, the bridge was determined to be stable, and the reduced wind loads played a significant contribution to controlling project costs. Having reduced the lateral loads in the project significantly was very important, but providing a suitable design to use a narrow, unreinforced spread footing still offered many challenges. Geotechnical engineers in the project accepted the task of limiting deflection of the pier, keeping eccentricity within the footing, and keeping peak foundation bearing pressures to acceptable thresholds. Using conventional analysis, meeting these criteria was not feasible without extensive foundation improvements. Ideas that were under consideration were major soils improvements around the piers, installing pipe pile upstream and downstream, and connecting those to the caissons. Another alternative that was proposed was to analyze the hours disregarded, as it may not be in place when needed to withstand the extreme loads. Due to the softness of surrounding soil and the variability of the soil response based on pier deflection, the resistance to the surrounding soils are typically left out of a conservative analysis also. This results in a simple spread footing on rock. In the case of Milton, Madison, that resulted in force resultants with eccentricity of over 20 feet, which was a problem because the caisson was only 20 feet wide. To address this, the engineers at Michael Baker proposed using finite element analysis that considered the response of the soils in supporting the pier and foundation against lateral loads. This was coordinated closely with Federal Highway, and a scour mitigation design was approved that would keep the surrounding soils where they were needed to improve foundation resistance. The proposed scour mitigation consisted of placing a 12-foot thick riprap shelf below the contraction scour depth. The depth and thickness was selected to avoid turbulence and to avoid being undercut by bed forms. High-performance geotextiles and large riprap were specified to resist local scour. The soft soils surrounding a spread footing are typically disregarded as part of conservative design practice. With the assumption that surrounding soils remain in place to improve foundation resistance, however, the loads of the bedrock were significantly reduced. This slide shows the load resistance with no surrounding soils considered and with the surrounding soils included. In the former scenario, the bedrock carries all the load, becoming very eccentric, resulting in overturning. With the soil considered in the analysis, as the pier deflects, the soft soil provides increased resistance, reducing the load in the bedrock. This more closely matches reality. The resultant load stayed within the foundation limits. The engineers at Michael Baker performed 3D finite element analysis with Midas GTS software to model the responses of the pier, caisson, soil, and rock. The soil and rock were modeled with more Coulomb failure criterion. The pier is modeled as an elastic solid, and the interfaces between the pier and the subsurface were modeled as standard friction interface. Here's some screen caps of that. The results of the analysis showed acceptable performance for the foundation. Maximum bearing stresses were less than the project's design criteria. Deflection of the pier stayed within the project's goals. This foundation never goes into tension, and eccentricity was determined to be acceptable. Determining if the existing soils and foundation can withstand modern loading demands was a huge hurdle cleared for the viability of cost-effective pier reuse. The next challenge was to transfer the loads into the soils and foundation. Two concerns to be addressed included tension in the under-reinforced stem and at the interface between the stem and the caisson, and also tension in the unreinforced caisson needed to be addressed. This slide shows compression and tension forces developed in the pier and caisson for various load combinations for the new wide-inch truss and piers. For service load combinations, the pier and caisson tended to remain in compression. For various strength and extreme event load combinations, the pier and caisson entered tension. To provide for 75-year service life, a variety of criteria were established for tension in the pier. These included goals of no tension for any service limit state and tension less than 95 psi for strength and extreme event load combinations. Wherever those criteria were not met, the caisson or stem would be strengthened and reinforced with reinforcing steel and a concrete shell. The strengthening would continue beyond the limit of the tension, plus the development length of the reinforcing steel. This sketch shows the pier strengthening that was eventually proposed. The proposal to strengthen the pier and holes would be cored deep into the unreinforced caisson with bundles of reinforcing steel grouted into the holes. Stem reinforcement would be continued onto the retrofitted caisson reinforcing, and a 24-inch minimum thickness high-performance concrete collar was installed around the existing pier stem. Final challenges to address include ensuring that the new original concrete would act as a composite structure. The pre-existing piers were supporting the weight of a 24-foot wide truss and would continue carrying that load throughout the construction of the pier encasement. With the existing truss removed, the previously loaded pier concrete would have a tendency to relax, creating interface shear between the new and old concrete. With the superstructure loads imparted through the bearings into only the widened pier cap, the new and old material would need to act in a composite manner to withstand these forces. To address these concerns, post-stressing was performed to the pier cap and stirrups were doweled into the existing pier throughout the height of the structure to provide composite performance and withstand shear forces at the interface. All right, I think I'm doing all right on time. That was a lot of discussion about the engineering that went into coming up with the solution of the project, or how to reuse the piers on the project. This project was built almost a decade ago. Technically, the substructure work that we're looking at here probably did happen about a decade ago. Construction was 2011 to 2013. I got some construction pictures here. This is down in the cofferdam. Looking here, I mentioned holes being doweled deep into the caissons and bundles of reinforcing steel being grouted into those. It was 3 number 14 bars that were bundled together at 3 feet spacing that got grouted into the caissons. One interesting thing that happened was that as Walsh was coring those 4-inch holes, the ties for the original caisson form were steel I-beams. So a rather unexpected thing that caused him to go through a lot of drill bits and take a lot of time was drilling through I-beams as they went down in those 4-inch core holes. It's a lot of coring too, approximately 70-foot deep caisson, I think 55 holes around the length of the caisson, so over 3,000 feet of drilling through concrete and steel beams. Here's a picture of the pier stem coming up from the caisson. I mentioned concerns about the interface between the new concrete and the old concrete and how that would react. Stirrups are basically specified to be installed at 2 feet vertical spacing and approximately 1 feet horizontal spacing, the entire length of the existing pier stem, to make sure that the new stem and the new concrete encasement and the old stem acted in a composite manner. Here's a picture coming up from the water. As mentioned previously, the original pier stems tapered inward to carry a 24-foot wide truss. The new pier stem is going to be a uniform shape up into the new pier cap, which would flare out. And then this is a picture of a mostly constructed pier. Again, the pier cap flares out to carry the 48-foot wide truss. It's also worth noting, and you may be able to see here, that they built the pier cap but left one piece of it incomplete. That was for a maintenance of traffic alternative that our design builder proposed as part of the selected team. It's kind of a side note to this presentation, but also one of the most fascinating aspects of the project. We procured this project, NDOT and KYTC did, in September 2010. And at the time, we were planning on the bridge being built, basically the substructure being constructed while traffic was still running on US 421, and then eventually the truss would be removed and a new truss constructed on top of the reconstructed piers. We were allowing design builders to have up to 365 days of closure to do that, but we also incentivized shorter construction or closure timeframes. I think at the time we'd done $25,000 per day for every day that they could shorten the closure timeframe. 4 of our 5 bidders bid 365 days. The 5th company, Walsh, bid 10 days, which we knew they were going that direction, but their proposal was to build temporary piers adjacent to the bridge, support the new truss, or build the new truss on the temporary piers, eventually route traffic onto that, before finally demoing the existing truss, then sliding the new truss into place. Is an extremely fascinating idea, amazing engineering on behalf of the Walsh and Buckland and Taylor and Burgess and Nipel team. And I do have a quick video to show of that. This is the bridge slide that was performed. Basically, as I mentioned, they had traffic running on that bridge on a temporary alignment. You can see the temporary foundations that they had constructed next to the permanent foundations. And actually, the foundation of the bridge was half temporary, and then they rested half of it on the new pier construction. Eventually shifting traffic over onto the new truss on the temporary alignment while they demoed the existing truss and finished their pier caps before finally doing this. This is basically pulled into place with equipment that would normally be lifting equipment. Ton of amazing engineering done by this team to make this work. I believe the 15,000 tons was the weight of the truss. 30 million pounds is what they pulled 55 feet into place to. This happened over the course of, I think, a little less than a day, if I recall. My memory is a little rusty. It's been 10 years at this point. But overall, an extremely fascinating project. I think that it was an amazing project from the beginning. Of all the concepts I talked about today with reusing the piers and the work that went into even being able to bring forward a project that was literally able to reduce project costs by close to half to reuse those piers and keep the truss on the existing alignment. But then certainly getting into construction and having the design builder propose this specific maintenance of traffic scheme definitely took the project to completely new levels. So thank you for the opportunity to present today. And I guess I need to move to the next slide.